What if I told you that something from before Earth even existed just passed through our solar system? And what if this ancient visitor is breaking every single rule we thought we knew about comets? July 1st, 2025. A telescope in Chile spots something that shouldn't be there. Scientists take a closer look and their jaws drop. This isn't just another space rock. This is 3I divided by Atlas, the third interstellar object ever discovered entering our solar system. And the data that just came back, it's absolutely insane. We're talking about a comet that's older than our entire solar system by billions of years. A comet that weighs more than 33 billion tons when it should weigh a fraction of that. A comet that's spewing chemicals that have never been seen in these combinations before. And here's the really crazy part. There's a 0.6% statistical chance that this exact same object might have sent the famous WOW signal back in 1977. Yeah, that WOW signal, the one that's been an unsolved mystery for almost 50 years. The scientific community is losing their minds right now, because every single observation of this thing reveals something that challenges what we thought we knew. James Webb just released data showing its atmosphere is completely backward from what it should be. The Hubble caught it doing something that has literally never been reported in any comet ever. And spacecraft near Mars and Jupiter are racing to get the closest views of this thing while they still can. So buckle up, because what I'm about to show you is going to completely change how you think about what's out there in space. This isn't just some regular comet passing by. This is a cosmic time machine that's been traveling through the galaxy since before our sun was even born, and it's carrying secrets that we're only just beginning to understand. Let me paint you a picture of what happened when astronomers first spotted this thing. It's the middle of the night in Chile. The Atlas Survey telescope is doing its routine scan of the sky, looking for anything unusual. Suddenly, a bright spot appears where nothing should be. At first, they think maybe it's a glitch. Maybe the equipment is acting up. But then, they check again. And again. And this thing is moving. Fast. Within hours, telescopes around the world are turning to look at this object. And as the data starts coming in, scientists are seeing numbers that don't make sense. The trajectory calculations show something that makes their hearts race. This object isn't from our solar system. It came from somewhere else in the galaxy. Somewhere far, far away. Now, you might be thinking, okay, so what? We've seen interstellar objects before, right? We had Oumuamua in 2017, that weird cigar-shaped thing that caused all sorts of debates. And we had Borisov in 2019, which looked more like a normal comet. So why is 3I divided by Atlas such a big deal? Here's why. When scientists calculated the mass of 3I divided by Atlas, they couldn't believe their eyes. This thing weighs over 33 billion tons. To put that in perspective, Oumuamua weighed maybe a few million tons. Borisov was bigger, maybe a billion tons. But 33 billion? That's not just bigger. That's 3 to 5 orders of magnitude more massive. In plain English, that means it's thousands to tens of thousands of times heavier than what we've seen before. And here's where it gets really weird. Based on what we know about how many heavy elements exist in our galaxy and how objects form, we should have seen around 100,000 smaller interstellar objects before we ever encountered something this massive. Think about that for a second. It's like if you were fishing in a lake and the very first fish you caught was a great white shark. That's not supposed to happen. The odds are completely against it. So immediately, scientists are asking questions. Why is this thing so big? Where did it come from? And most importantly, what is it made of? The answers to those questions are going to blow your mind. Let's start with where this thing came from, because this is where the story gets really fascinating. When astronomers trace back the trajectory of 3I divided by Atlas, they're not just looking at where it came from in space. They're looking at where it came from in time. The velocity measurements and the path this comet is taking tell us something incredible. This object didn't come from a nearby star system. It didn't come from some relatively young part of the galaxy. No, 3I divided by Atlas came from what astronomers call the thick disk of the Milky Way. Now, let me explain what that means, because this is important. Our galaxy isn't just a flat disk of stars. It's more like a layered structure. You've got the thin disk where our sun lives, which is relatively young and contains stars that formed more recently. But above and below that thin disk, there's an older population of stars called the thick disk. These stars formed during what scientists call the galaxy's cosmic noon, a period of intense star formation that happened between 9 and 13 billion years ago. Our solar system? It's only 4.5 billion years old. That means 3I divided by Atlas predates everything we know by more than 7.6 billion years. Let that sink in for a moment. This comet was already ancient when the cloud of gas and dust that would eventually become our sun was just starting to collapse. It was already wandering through space when the first dinosaurs on Earth were still billions of years away from existing. This is a cosmic time capsule, a messenger from an era of our galaxy that we've never been able to directly study before. Every comet we've ever observed formed in our solar system. Every single one came from the same materials, the same conditions, the same time period. But 3I divided by Atlas, it formed in a completely different environment, in a completely different era, possibly around a star that doesn't even exist anymore. And that brings us to what this thing is made of, because that's where things go from fascinating to absolutely mind-blowing. August 6th, 2025. The James Webb Space Telescope, the most powerful infrared telescope ever built, turns its gaze toward 3I divided by Atlas. The scientists operating Webb know they're about to get the most detailed chemical composition data ever obtained from an interstellar object. But they have no idea just how strange that data is going to be. Webb's instruments analyze the light coming from the cloud of gas and dust surrounding the comet's nucleus, what astronomers call the coma, and what they find makes them double-check their equipment, then triple-check it, because what they're seeing shouldn't exist. The coma of 3I divided by Atlas is dominated by carbon dioxide, not water, not the mix of ices you'd expect. Carbon dioxide. The measurements show a carbon dioxide to water ratio of 7.6 to 1. In plain terms, that means for every tiny bit of water ice in this comet, there's more than 7 times as much carbon dioxide ice. Now, why is that weird? Because every other comet we've ever studied, and we're talking about hundreds of comets from our solar system, shows the opposite pattern. Comets are typically made mostly of water ice, with some carbon dioxide mixed in. But 3I divided by Atlas is 95% carbon dioxide and only 5% water. That's completely backward. And it gets stranger. Webb also detected almost no carbon monoxide, which is another chemical you'd normally expect to find in comets. There's also carbonyl sulfide in there, but in tiny amounts. The chemical composition is unlike anything scientists have ever encountered. So, what does this mean? Why would a comet have this bizarre chemistry? Scientists have come up with 2 main ideas, and both of them are fascinating. The first theory is about radiation. Think about this. 3I divided by Atlas has been wandering through interstellar space for billions of years. That's billions of years of being bombarded by cosmic rays, high-energy particles that zip through the galaxy at nearly the speed of light. These cosmic rays are like tiny bullets that can break apart molecules. And here's the key. They're especially good at destroying the more delicate, volatile compounds. Water ice is actually pretty tough. It can survive a lot of radiation damage. But compounds like carbon monoxide, they break down more easily. So the theory is that over billions of years, the constant cosmic ray bombardment selectively destroyed the more fragile molecules in 3I divided by Atlas, leaving behind the more stable carbon dioxide. It's like if you left different materials out in the sun for years. Some would degrade and fall apart, while others would remain intact. But there's a second theory, and this one is even more interesting. It's possible that 3I divided by Atlas formed in a very specific location in its original protoplanetary disk, the cloud of gas and dust around a young star where planets and comets form. Every protoplanetary disk has what astronomers call ice lines. These are specific distances from the star where it gets cold enough for different chemicals to freeze. Close to the star, it's too hot for anything to freeze. A bit farther out, water freezes. Even farther out, carbon dioxide freezes. And way out at the edge, even carbon monoxide freezes. The theory is that 3I divided by Atlas formed right at the carbon dioxide ice line. At this exact location, carbon dioxide was freezing out of the gas and accumulating, but the comet was still too warm for significant amounts of carbon monoxide to stick around. So from the moment it was born, 3I divided by Atlas was rich in carbon dioxide and poor in other volatiles. Either way, whether it's billions of years of radiation damage or the specific conditions where it formed, what we're looking at is a comet that represents fundamentally different formation conditions than anything in our solar system. It's proof that planetary systems across the galaxy don't all look the same. The ingredients, the chemistry, the building blocks, they can vary wildly depending on when and where a system forms. And as if that wasn't strange enough, there's another chemical mystery that has scientists absolutely baffled. August to September 2025. The Very Large Telescope in Chile, one of the most powerful optical telescopes on Earth, is tracking 3I divided by Atlas as it gets closer to the Sunday. The astronomers are using spectroscopy, basically. They're splitting the light from the comet into its component wavelengths to see what elements are present in the gas around it. And they find something that shouldn't be possible. They detect nickel, lots of nickel vapor. But here's the thing, they detect almost no iron. Now, if you know anything about astronomy, you know that nickel and iron are always found together. Always. They're created together in supernova explosions when massive stars die. They're locked together in meteorites. Every asteroid, every meteorite, every natural space rock we've ever studied shows nickel and iron together in predictable ratios. Seeing nickel without iron is like finding someone's left shoe but not their right shoe. It just doesn't happen in nature. At first, when 3I divided by Atlas was still far from the sun, more than 2.64 astronomical units away, which is about 2.6 times the Earth-Sun distance, the spectroscopic observations showed only nickel absorption lines. No iron. As the comet got closer and passed that 2.64 AU threshold, suddenly iron started appearing. The nickel to iron ratio shifted dramatically. So what's going on? How can you have nickel without iron? The answer involves some really exotic chemistry. Scientists think that 3I divided by Atlas contains organometallic compounds. Now, that's a fancy term, but let me break it down. Organometallic compounds are molecules where a metal atom is bonded to carbon-containing groups. And there are two specific organometallic compounds that might explain what we're seeing: nickel tetracarbonyl and iron pentacarbonyl. These are molecules where nickel or iron atoms are bonded to 4 or 5 carbon monoxide molecules. They form in very cold, carbon monoxide-rich environments. And here's the crucial part: they have different sublimation points. Sublimation is when a solid turns directly into a gas, skipping the liquid phase. Nickel tetracarbonyl sublimes at a much lower temperature, around 74 to 82 Kelvin, which is about -199 to -191 degrees Celsius. Iron pentacarbonyl needs more heat. It sublimes at 97 to 108 Kelvin, or -176 to -165 degrees Celsius. So as 3I divided by Atlas got closer to the sun and warmed up, the nickel compound started sublimating first, releasing nickel atoms into the coma. That's why astronomers saw nickel without iron at first. Then, as the comet got even closer and warmer, the iron compound started sublimating too, and iron appeared. The temperature difference between these two compounds explains the sequence of observations perfectly. But here's what makes this so significant. The presence of these organometallic carbonyls suggests that 3I divided by Atlas formed in extremely cold conditions with abundant carbon monoxide. These are the kind of conditions you'd expect in the outer reaches of a protoplanetary disk billions of years ago, in a region of the galaxy where the chemistry was fundamentally different from what we have in our solar system today. Now, I have to mention something here because it's been making the rounds in the news. Some people, including Harvard astrophysicist Avi Loeb, have pointed out that these organometallic processes, specifically producing nickel without iron, are actually used in industrial settings on Earth. The Mond process, used in nickel refining, produces pure nickel using nickel carbonyl. And some have suggested that maybe, just maybe, what we're seeing isn't natural. But here's the thing, and this is important. The overwhelming consensus among astronomers is that 3I divided by Atlas is absolutely a natural object. Yes, the chemistry is unusual. Yes, it's different from what we typically see. But unusual doesn't mean artificial. The universe is a weird place, and there are plenty of natural processes that can create chemistry we don't see in our own backyard. The organometallic carbonyl explanation works perfectly with natural formation in the ancient thick disk of the galaxy, and there's no need to invoke anything else. Still, the fact that we're even having these conversations shows just how strange this object is. It's pushing the boundaries of what we thought was possible in natural comet chemistry. But we're not done with the weird observations yet. Not even close. Let's talk about water. Or more specifically, let's talk about the absolutely insane amount of water that 3I divided by Atlas is losing. Late July and August 2025. NASA's Neil Gehrels Swift Observatory, a space telescope that observes in ultraviolet wavelengths, detects something remarkable. It picks up hydroxyl emission from 3I divided by Atlas. Hydroxyl, that's OH, just water without one of its hydrogen atoms, is a telltale sign of water molecules being broken apart by sunlight. The measurements are shocking. 3I divided by Atlas is producing approximately 1.36 times 10 to the 27th power water molecules per second. Let me translate that into something more understandable. That's 40 kilograms of water every single second. To put it in even simpler terms, scientists describe it as a fire hose running at full blast, constantly spraying water into space. Now, losing water isn't unusual for comets. That's what comets do. As they get close to the sun, they warm up, their ices sublimate, and they create those beautiful tails we see from Earth. But here's what makes 3I divided by Atlas special. This water activity was detected when the comet was 2.9 astronomical units from the Sunday. That's almost 3 times farther than Earth's orbit. At that distance, it's cold. Way too cold for most comets to show significant water activity. Typically, comets don't start producing large amounts of water vapor until they get inside 2.5 AU. And even then, the activity is usually pretty modest until they get much closer. But 3I divided by Atlas is gushing water at a distance where it should barely be active at all. The inferred water production rate suggests that at least 7.8 square kilometers of the comet's surface is actively releasing water. Given that the nucleus is estimated to be around 2.8 kilometers in diameter, with a total surface area of maybe 25 square kilometers, that means over 8% of the entire surface is actively outgassing. Some estimates suggest it could be as high as 20% or more. For comparison, most comets show active areas covering 3% to 5% of their surface. 3I divided by Atlas is more than twice as active as it should be, at a distance where it shouldn't be active at all. This is what astronomers mean when they call it hyperactive. So, what's going on? How can this comet be losing so much water when it's still so far from the sun? The answer lies in something scientists call icy grain fountains, and this is where things get really cool. Pun intended. When comets are far from the sun, the surface of the nucleus is way too cold for efficient sublimation. The ice is frozen solid. But here's what happens. As the comet rotates and orbits, sunlight heats small areas of the surface. Pockets of more volatile materials underneath the surface can suddenly sublimate, and when they do, they can violently erupt, blowing chunks of ice off the surface and into space. These aren't tiny ice crystals. We're talking about chunks of water ice, some potentially quite large, getting ejected from the nucleus. Once these ice chunks are floating in space, surrounded by vacuum, they have a much larger surface area exposed to sunlight. And even though the sunlight is weak at 2.9 AU, it's enough to slowly sublimate these ice grains. So what you end up with is this. The nucleus itself might not be sublimating much water because it's too cold, but the cloud of ice chunks surrounding the nucleus, they're acting like millions of tiny steam vents, each one slowly releasing water vapor as they warm up in the sunlight. This creates an extended source of water vapor that makes the comet appear far more active than its distance from the sun would suggest. Near-infrared observations from the Gemini South Telescope and NASA's Infrared Telescope facility confirmed the presence of these water ice grains floating in the coma. They could actually see the signature of solid water ice suspended in space around the comet. This mechanism, icy grain fountains, explains the hyperactivity, but it also raises questions. Why is 3I divided by Atlas producing so many ice chunks? Is it because of its unique composition with all that carbon dioxide? Is the carbon dioxide sublimating more easily and dragging water ice with it? Is the ancient radiation-damaged structure of the nucleus making it more fragile and prone to breaking apart? These are questions scientists are still trying to answer. But one thing is clear. 3I divided by Atlas is not behaving like a normal comet, even for an interstellar visitor. And just when you think you've seen everything this comet can throw at you, it does something that has literally never been observed before. September 7th, 2025. Astronomers noticed something strange in the images of 3I divided by Atlas. Up until this point, all the spectroscopic observations had suggested the comet appeared reddish, similar to dusty comets in our solar system. But suddenly, dramatically, the comet transforms. It develops a distinctive green glow. Now, green comets aren't unheard of. Many comets develop a green color as they approach the Sunday. But the timing and intensity of 3I divided by Atlas's green transformation was unexpected. The green color comes from cyanogen, that's CN, a molecule made of one carbon atom and one nitrogen atom. And here's what's happening. Deep inside the comet's nucleus, there's hydrogen cyanide ice. Hydrogen cyanide is HCN, hydrogen, carbon, and nitrogen bonded together. As the comet warms, this hydrogen cyanide ice sublimates, turning directly from a solid into a gas. Once it's in the gas phase, ultraviolet light from the sun breaks the HCN molecules apart. The hydrogen floats away, but the carbon and nitrogen remain bonded as cyanogen. Now, when sunlight hits these cyanogen molecules floating in the coma, something called fluorescence occurs. The molecules absorb certain wavelengths of light and then re-emit that energy at different wavelengths. Cyanogen specifically emits at wavelengths that appear green to our eyes. It's the same phenomenon that causes fluorescent materials to glow under black lights. Observations from the Very Large Telescope captured this chemical transformation in detail. At a distance of 2.85 AU from the Sun, the comet was producing about 10 to the 23.6 1-power cyanide molecules per second. But here's the crazy part. The production rate was scaling dramatically with distance. The measurements showed that for every time the comet's distance from the Sun was cut in half, the cyanide production increased by a factor of 2,700. By mid-August, the cyanide production rate had climbed to around 8 times 10 to the 23rd power molecules per second. That's 800 million trillion cyanide molecules every second. The comet was essentially erupting cyanide as it warmed. Now, before anyone panics, cyanide in space is not dangerous to us. It's spread out over millions of cubic kilometers and poses absolutely no threat to Earth. But what it does tell us is something really interesting about the comet's chemistry and history. Scientists classify comets based on their chemistry, and one of the key measurements is the ratio of diatomic carbon to cyanogen, that's C2 to Cn. 3I divided by Atlas shows strong carbon chain depletion, meaning it has very little C2 compared to Cn. This classification indicates that the comet has preserved its primordial chemical composition since it formed billions of years ago. This is significant because it suggests that 3I divided by Atlas formed in a different region of its original protoplanetary disk compared to typical comets in our solar system. Different regions of a protoplanetary disk have different temperatures, different pressures, and different chemical abundances. Where a comet forms determines what chemicals get incorporated into it. And 3I divided by Atlas's chemistry is telling us it formed somewhere very different from where our solar system's comets formed. The green glow is more than just a pretty color. It's a chemical fingerprint that reveals the comet's ancient origins. But there's one more visual anomaly we need to talk about, and this one is truly bizarre. July 21st, 2025. The Hubble Space Telescope captures high-resolution images of 3I divided by Atlas. The astronomers are looking for the typical features of a comet, a bright nucleus, a glowing coma, and a tail streaming away from the sun as solar wind and radiation pressure push gas and dust away from the comet. They find all of those things, but they also find something else, something that has never been reported before in any solar system comet. An anti-tail. Let me explain what that means. Normal comet tails always point away from the Sunday. This makes sense, right? The solar wind, the stream of charged particles flowing out from the sun, pushes the gas in the coma away from the comet, creating a gas tail that points directly away from the Sunday. Radiation pressure from sunlight pushes the dust particles away, creating a dust tail that also points away from the sun, though usually at a slightly different angle because the dust particles have more momentum. But an antitail? That's a structure that extends toward the sun, not away from it. It's pointing in the wrong direction. Harvard astrophysicist Avi Loeb described it as an extension of the scattered sunlight around 3I divided by Atlas that extends toward the sun rather than away from it. And this isn't just a trick of perspective or viewing geometry. This is real material extending sunward. So, how is this possible? How can you have material flowing toward the sun instead of away from it? The answer goes back to those icy grain fountains we talked about earlier. Remember, 3I divided by Atlas is ejecting chunks of ice from its nucleus. While the comet is primarily made of carbon dioxide by mass, about 87%, the longest surviving grains in the coma are made of water ice because water ice evaporates more slowly than carbon dioxide ice. These water ice fragments are sublimating gradually as they drift through space. But here's the key. The side of each ice grain facing the sun receives more heating than the side facing away. This means the sunward side sublimes faster, which creates a kind of rocket effect. The ice grain loses more mass on the sun-facing side, which can actually give it a tiny push in the direction of the Sunday. Additionally, larger ice fragments can survive for considerable distances before completely evaporating. As they slowly drift and sublimate, they create a glow from scattered sunlight. The largest fragments, the ones that survive the longest, can travel far enough to create a visible extension in the sunward direction. This creates what we're seeing, an antitail. It's an extension of what astronomers call the snow line, the survival distance for sublimating ice grains, but extending in the direction of the sun rather than away from it. This is a totally new phenomenon. It provides direct evidence that 3I divided by Atlas is shedding substantial amounts of solid icy particles that persist in space longer than expected. And it's another reminder that this comet is full of surprises. Now, all of these ground-based and space-based observations from Earth are incredible. We've learned so much about 3I divided by Atlas in just a few months. But there's a problem. As the comet approached perihelion, its closest point to the Sun, on October 29, 2025, it became nearly impossible to observe from Earth. The reason is simple geometry. At perihelion, 3I divided by Atlas was on the opposite side of the Sun from Earth. The solar elongation, the angle between the Sun and the comet as seen from Earth, was only 12.8 degrees. That means to see the comet, you'd have to look almost directly at the Sun, which is impossible with most telescopes. The glare from the Sun would overwhelm any light from the comet. This is frustrating because perihelion is when comets are at their most active. The heat from the Sun is at maximum, sublimation is at its peak, and all the interesting chemical processes we've been discussing are happening at their most intense. And we couldn't watch it from Earth. But here's where the story gets really exciting. Because while Earth was in the wrong position, several spacecraft scattered throughout the solar system were perfectly positioned to observe 3I divided by Atlas during its most active period. October 17th, 2025. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express, both in orbit around Mars, turned their instruments toward 3I divided by Atlas. On October 3rd, the comet had passed within 30 million kilometers of Mars. That's about 18.6 million miles, or roughly 20% of the distance from Earth to the Sunday. This was close enough for the orbiter's cameras and spectrometers to get a good look. The ExoMars Trace Gas Orbiter's color and stereo surface imaging system, called CASIS, successfully photographed the comet. The images showed a fuzzy white dot surrounded by a clearly visible coma. The nucleus itself was still too distant and too small to resolve as more than a point of light, but the coma structure was beautifully captured. These are the closest images of 3I divided by Atlas obtained by any ESA mission. But Mars wasn't the only vantage point. September 4th, 2025. NASA's Psyche spacecraft, on its way to the metallic asteroid 16 Psyche, passed within 0.302 astronomical units of 3I divided by Atlas. That's about 45.2 million kilometers or 28 million miles. Psyche's cameras captured images of the comet from this relatively close distance, providing another perspective that would have been impossible from Earth. And then there's the really exciting observation campaign. November 2nd through 25th, 2025. The European Space Agency's Jupiter Icy Moons Explorer, called JUICE, observed 3I divided by Atlas using 5 different instruments. JUICE has cameras for visible light, instruments for near-infrared imaging, an ultraviolet spectrometer to analyze the composition of the coma, a sub-millimeter instrument to detect various molecules, and even a neutral atom sensor that can detect particles in the comet's environment. This multi-instrument observation campaign happened right during the comet's most active period, just after perihelion when activity was at maximum. JUICE was able to capture data on the coma structure, the gas composition, the dust distribution, and the overall behavior of the comet during this critical time. Now, here's the thing. JUICE is on the opposite side of the sun from Earth, and it's so far away that radio signals take a long time to reach us. The data that JUICE collected during November 2025 won't reach Earth until February 2026. So, as I'm telling you this story, that data is still traveling through space. Scientists are waiting eagerly to see what it reveals. This multi-spacecraft campaign represents something unprecedented in the history of comet observation. We've never had this many different spacecraft, from this many different vantage points, observing an interstellar visitor during its closest approach to the Sun. Each spacecraft has different instruments, different capabilities, and different perspectives. When all of this data is combined and analyzed, we're going to get the most complete picture ever obtained of an interstellar object. But even before the JUICE data arrives, we already know something remarkable from the Mars observations. 3I divided by Atlas remained active and continued showing all of its unusual characteristics right through perihelion. The predictions about its behavior were confirmed. This wasn't a normal comet that just happened to come from interstellar space. This was something fundamentally different. Now, here's another fascinating aspect of this story that most people don't know about. 3I divided by Atlas was actually observed before it was officially discovered, and those early observations are incredibly valuable. May 7th through June 2nd, 2025. The Transiting Exoplanet Survey Satellite, TESS, was doing its job, which is to stare at sections of the sky looking for planets around other stars. TESS looks for tiny dips in starlight that happen when a planet passes in front of its host star. But while it was doing that, it happened to capture 3I divided by Atlas in its field of view. At the time, nobody knew the comet was there. TESS was just collecting data. But later, after 3I divided by Atlas was discovered on July 1st, astronomers went back through the TESS data and found the comet in images from almost 2 months earlier. The TESS observations showed the comet gradually brightening from magnitude 20.9 to 19.57 over that time period. For those not familiar with astronomical magnitude, smaller numbers mean brighter objects. So the comet was getting brighter as it got closer to the Sunday, and importantly, TESS showed signs of faint coma activity even when the comet was beyond 4.5 astronomical units from the Sun, far beyond where most comets start showing activity. But TESS wasn't the only serendipitous observation. The Zwicky Transient Facility, ZTF, another survey telescope, had captured images of 3 I divided by Atlas on May 21, 2025. And digging even further back, Atlas telescopes had imaged it on March 28, 2025. That's more than 3 months before the official discovery. These early observations showed that the comet was already producing a coma when it was far from the Sun, confirming that its unusual activity started early and persisted throughout its journey through the inner solar system. There's an interesting reason why these early observations didn't lead to an immediate discovery. During this time period, 3 I divided by Atlas was passing in front of the dense star fields of the galactic center, the central bulge of the Milky Way where stars are packed incredibly close together. Trying to spot a faint, moving comet against that crowded background is like trying to find a specific firefly in a swarm of thousands. The comet likely went unnoticed for weeks or even months, because it was lost in the glare and confusion of all those background stars. But once astronomers knew where to look and went back through archival data, they could piece together the comet's activity profile going back months before discovery. This extended baseline of observations is invaluable for understanding how the comet behaved as it approached the Sunday. Now, we need to talk about something controversial. Something that's been making headlines and sparking debates online. And I want to be very clear about the facts here, because this is where things can get sensationalized. August 15th, 1977. Almost 50 years ago, Ohio State University's Big Ear Radio Telescope was scanning the sky as part of the Search for Extraterrestrial Intelligence SETI. At 11:16 p.m., the telescope detected a strong narrowband radio signal. The signal lasted for 72 seconds, exactly the maximum length of time the telescope could observe any point in the sky before the Earth's rotation moved that point out of view. The signal was so strong and so unusual that when astronomer Jerry Amon reviewed the computer printout a few days later, he circled it and wrote, "Wow," in the margin. That's how it got its name, the WOW signal. For nearly 50 years, the WOW signal has remained one of astronomy's greatest mysteries. Despite numerous attempts, it was never detected again. Many natural explanations have been proposed: hydrogen clouds, passing comets, Earth-based interference, but none of them perfectly fit the observations. Now, here's where 3 I divided by Atlas comes into the picture. Harvard astrophysicist Avi Loeb, who's known for proposing unconventional ideas about interstellar objects, did a calculation. He traced back the orbit of 3 I divided by Atlas to figure out where it was in 1977. And what he found was striking. 3 days before the WOW signal was detected, 3 I divided by Atlas was located at coordinates within 9 degrees of the signal's origin. The calculation showed the comet was approximately 4 degrees off in right ascension and 8 degrees off in declination from where the WOW signal came from. Now, 9 degrees might sound like a big distance, but in astronomical terms, it's actually quite close. The probability of 2 random directions in the sky being aligned to that level, about 0.6%. That's pretty low. It's statistically significant enough to raise eyebrows. Loeb went further. He calculated that if the WOW signal had originated from 3I divided by Atlas when it was about 600 times the Earth-Sun distance away, the signal would have required a transmitter power of about 0.52 gigawatts. For reference, that's roughly the output of a typical nuclear power plant on Earth. The frequency of the WOW signal, 1420.4556 MHz, showed a blue shift of about 10 kilometers per second toward Earth. Loeb noted that this is the same order of magnitude as, though smaller than, 3I divided by Atlas's approach velocity of 60 kilometers per second toward the Sunday. So on the surface, there are these tantalizing coincidences. The comet was in approximately the right place in the sky. The power requirements could fit with technology we understand. The frequency shift is in the ballpark. But, and this is a really important but, we need to be extremely careful here about jumping to conclusions. First, let's talk about that 9-degree difference. Yes, 0.6% is a low probability. But here's the thing about statistics. Unlikely coincidences happen all the time when you're looking at enough data. With billions of objects in the sky and decades of astronomical observations, you're going to find some alignments that seem meaningful just by pure chance. Second, the WOW signal came from a very specific point in the sky, but the Big Ear telescope's beam was actually quite wide. The uncertainty in the exact origin of the signal is larger than people often realize. And when you factor in that uncertainty, plus the position uncertainty of where 3I divided by Atlas was in 1977, that 9-degree gap becomes more significant. Third, and this is crucial, the overwhelming scientific consensus is that 3I divided by Atlas is a completely natural comet. Every single observation we've discussed, the unusual chemistry, the nickel-iron separation, the hyperactive water production, the antitail, all of these can be explained through natural processes. Weird natural processes, yes. Unprecedented in some cases, absolutely. But still natural. The strange chemical composition makes perfect sense if the comet formed billions of years ago in the thick disk of the galaxy under very different conditions than our solar system. The organometallic carbonyls explain the nickel without iron observations. The icy grain fountains explain the hyperactivity. Everything fits with it being an ancient, exotic, but fundamentally natural object. There's no evidence whatsoever that 3I divided by Atlas has any artificial structures, any propulsion systems, any deliberate course corrections, or any characteristics that would suggest it's anything other than a comet. And remember, before anyone suggests this could be some kind of probe or artificial object, we have the technology to detect those things. Our instruments are sophisticated enough that if there were artificial materials or structures, we'd see them. As for the WOW signal itself, there have been numerous proposed natural explanations over the years. Some astronomers have suggested it could have been caused by a hydrogen cloud that was at the right position and velocity to produce the signal. Others have pointed to comets, though not 3I divided by Atlas specifically, as possible sources, since comets can release hydrogen that could theoretically produce similar signals. The reality is that we may never know for certain what caused the WOW signal. It happened almost 50 years ago. It was never repeated, and we don't have the detailed follow-up observations we would need to definitively identify the source. So, is the alignment between 3I divided by Atlas and the WOW signal interesting? Absolutely. Is it worth noting and investigating? Sure. Could it be a meaningful connection? It's possible, though unlikely. But does it mean that 3I divided by Atlas is artificial, or that we found evidence of extraterrestrial technology? No, not at all. That would require extraordinary evidence, and we simply don't have it. The scientific method requires that we follow the evidence wherever it leads. And right now, all the evidence points to 3I divided by Atlas being a natural object. A weird one, an unprecedented one, an ancient cosmic wanderer with chemistry we've never seen before, but natural nonetheless. And honestly, that's amazing enough. We don't need to invoke aliens to make this story incredible. The real story that we're studying, a 7.6 billion-year-old time capsule from the ancient galaxy, is already mind-blowing. Now, let's step back and look at the big picture of everything we've learned about 3I divided by Atlas. Because when you put it all together, what you're seeing is a revolution in our understanding of interstellar objects and planetary system formation. Before 2017, we had never detected an interstellar object passing through our solar system. Not one. Astronomers had theorized that they should exist. If planetary systems are common throughout the galaxy, then occasionally an object should get ejected from one system and wander through space until it encounters another system. But theory is one thing. Actually finding one is something else entirely. Then, Oumuamua showed up in 2017, and everything changed. For the first time, we had proof that interstellar objects do indeed pass through our solar system. Oumuamua was bizarre. That elongated shape, the way it accelerated slightly as it left the solar system, the unusual reflectivity. It sparked debates and controversies that continue to this day. 2 years later, in 2019, we found Borisov. This one looked more like a normal comet, which was almost a relief after the weirdness of Oumuamua. Borisov had a coma. It had a tail. It acted like comets should act. It was like meeting an alien and discovering they were pretty similar to us after all. But now we have 3I divided by Atlas, and it's showing us that the truth is somewhere in between. It's definitely a comet. It has all the characteristics we'd expect. But those characteristics are cranked up to 11 with chemistry and behavior that pushes the boundaries of what we thought was possible. And here's what this tells us. Planetary systems across the galaxy are diverse. Not all star systems form the same way. The conditions in the protoplanetary disk around a star depend on when that star formed, where in the galaxy it formed, what heavy elements were available at that time, and countless other factors. Our solar system formed 4.5 billion years ago from a cloud of gas and dust that had been enriched by previous generations of stars. By that point in galactic history, there had been billions of years of star formation and stellar death, creating and dispersing heavy elements throughout the galaxy. The chemical composition of our solar system reflects that history. But 3I divided by Atlas formed much earlier, possibly more than 9 billion years ago, when the galaxy was fundamentally different. There were fewer heavy elements. The star formation rate was much higher. The dynamics of the galaxy were different. And all of those factors influenced how protoplanetary disks formed and what kind of objects condensed out of them. What we're seeing with 3I divided by Atlas is a direct sample of that ancient era. Every measurement we take, the carbon dioxide dominance, the organometallic carbonyls, the carbon chain depletion, is giving us information about planetary formation conditions during the galaxy's cosmic noon. This is data we could never get any other way. We can't travel 9 billion years back in time. We can't easily observe protoplanetary disks around ancient stars because most of those stars are gone. But 3I divided by Atlas? It's a preserved sample, a frozen record of that distant time. And it's teaching us that the building blocks of planetary systems, the comets, asteroids, and planetesimals that eventually collide and accrete to form planets, varied much more wildly across the galaxy's history than we imagined. Think about what this means for the search for life elsewhere in the universe. The chemistry available in a planetary system depends on what's available in the protoplanetary disk. If comets in ancient systems had completely different compositions than our comets, more carbon dioxide, different organic compounds, different volatile inventories, then the planets that formed in those systems would have received a different mix of chemicals when those comets bombarded them. Earth's water probably came from comets and asteroids that impacted early in our planet's history. The organic compounds that eventually led to life, amino acids, sugars, all those complex carbon-based molecules, many of them were likely delivered by comets. If the comets in other systems have radically different chemistry, then the early planets in those systems would have started with a different chemical palette. Does that make life more likely or less likely? We don't know yet. But what we do know is that the chemical diversity of planetary systems is greater than we thought, which means the pathways to complex chemistry and potentially to life might be more varied than we imagined. Some planetary systems might be rich in water. Others might be carbon dioxide rich, like 3i divided by Atlas suggests is possible. Others might have different volatile inventories entirely, and each different starting condition leads to a different chemical evolution. This is why studying interstellar objects is so important. Each one is a data point. Each one tells us something about the diversity of planetary systems throughout the galaxy. And the more we learn about that diversity, the better we can understand our own place in the cosmic story. Now let's talk about the mass problem, because this is one of the most puzzling aspects of 3i divided by Atlas, and it raises some really deep questions. Remember, 3i divided by Atlas weighs over 33 billion tons. That's orders of magnitude more massive than Oumuamua or Borisov. And based on our understanding of how many heavy elements exist in the galaxy and how interstellar objects should be distributed, we should have seen tens of thousands or even 100,000 smaller objects before encountering something this large. It's a statistical anomaly. And whenever you see a statistical anomaly, you have to ask, is this just bad luck or is something wrong with our assumptions? There are a few possible explanations. One is that we simply got lucky or unlucky, depending on how you look at it. Statistics are just probabilities. Sometimes unlikely things happen. You can flip a coin and get heads 10 times in a row. It's unlikely, but it's possible. Maybe 3i divided by ATLAS just happened to be the first large interstellar object to pass close enough to Earth for us to detect, even though smaller ones have been passing by unnoticed. But there's another possibility that's more interesting. Maybe our detection methods are biased toward finding larger objects. Think about it. 3i divided by Atlas is bright because it's big and active. It produces a huge coma. It's easy to spot in telescope surveys. But a small, dark, inactive interstellar object? That would be incredibly difficult to detect. It would be faint. It would move slowly across the sky compared to objects in our solar system, and it wouldn't have any of the bright activity that makes comets stand out. It's possible, maybe even likely, that hundreds or thousands of smaller interstellar objects have passed through our solar system without being detected. They came, they passed by, they left, and we never knew they were there. We only noticed the big, bright, active ones like 3i divided by Atlas. This is called detection bias, and it's a huge problem in astronomy. You can only study what you can see, and if your instruments are better at seeing certain types of objects, then your observations will be skewed toward those objects. It's like trying to understand what fish live in a lake by only using a net with large holes. You'll catch the big fish, but all the small ones will slip through and you'll incorrectly conclude that only big fish exist. If this is true, it means that interstellar objects passing through our solar system might be far more common than we realize. There might be dozens passing through right now that we're not detecting. And if that's the case, it changes our understanding of how much material is wandering between star systems in the galaxy. Some astronomers estimate that there could be trillions of interstellar objects in the galaxy at any given time. Comets and asteroids ejected from their home systems, drifting through interstellar space for millions or billions of years until they eventually encounter another star system. The galaxy might be full of these wanderers, crisscrossing space, carrying samples from one stellar neighborhood to another. And here's a wild thought. If interstellar objects are common, and if they've been traveling between star systems for billions of years, then they could be mixing and distributing material throughout the galaxy. A comet ejected from one system could eventually be captured by another system. Organic compounds formed around one star could end up on planets around a completely different star. This process is called panspermia, the idea that life, or at least the chemical precursors to life, could be distributed throughout the galaxy by natural processes. Now, to be clear, panspermia is highly speculative. We have no direct evidence that it actually happens. But the fact that interstellar objects exist and travel between star systems means it's at least physically possible. Could the building blocks of life on Earth have originally come from another star system, carried here by an ancient comet like 3I divided by Atlas? We don't know, but it's an incredible thought that we might be connected to other worlds not just by physics and chemistry, but by actual physical transfer of material across light years of space. Let me bring all of this together, because there's an even bigger story here about what 3I divided by Atlas represents for the future of astronomy. Right now, we've detected exactly 3 interstellar objects. That's not a lot of data, but new telescope systems are coming online that are going to change everything. The Vera Rubin Observatory, which is scheduled to start operations soon, will survey the entire visible sky every few nights. It's going to be incredibly sensitive and will detect faint, fast-moving objects that current surveys would miss. Astronomers estimate that once Vera Rubin is operational, we might detect dozens or even hundreds of interstellar objects per year. Instead of getting one every couple of years, we'll be drowning in data. We'll be able to build up statistical samples. We'll be able to compare objects and look for patterns. We'll be able to answer questions like, are most interstellar objects like 3I divided by Atlas with bizarre chemistry? Or is 3I gedeeld door Atlas unusual even among interstellar visitors? And here's where things get really exciting. If we can detect interstellar objects early enough in their journey through our solar system, we might be able to send spacecraft to intercept them. Instead of just observing them from a distance with telescopes, we could actually go there. We could take close-up images. We could analyze the surface directly. We could even collect samples and bring them back to Earth. Imagine having pieces of 3I divided by Atlas in a laboratory here on Earth. Imagine being able to analyze the ice structure, the chemistry, the mineral composition with the full range of equipment we have available on the ground, instead of being limited to what we can see through telescopes. The scientific return from a sample return mission to an interstellar object would be incredible. NASA and ESA have both studied concepts for interstellar object intercept missions. The challenges are enormous. You have to detect the object early, you have to launch a spacecraft quickly before the object leaves the solar system, and you have to have enough fuel to match velocities with something that might be traveling at 60 kilometers per second relative to the sun day. But it's technically possible with current or near future technology. And if we could pull it off, If we could actually bring back samples from an object like 3I divided by Atlas, it would be one of the greatest scientific achievements in history. We would have in our hands material that formed billions of years before our solar system, around a star that might not even exist anymore, in a region of the galaxy we can never visit. It would be like having a time machine. These are the kinds of missions that scientists are dreaming about now. And with each new interstellar object we detect, we learn more about how to design those missions. 3I divided by Atlas has taught us so much about what to expect. The activity levels, the chemistry, the behavior. Future missions will benefit from this knowledge. We're living in the early days of interstellar object astronomy. Just like the early days of exoplanet detection in the 1,990 seconds, when we went from knowing of no planets around other stars to detecting hundreds and then thousands, we're at the beginning of a similar revolution with interstellar objects. And 3I divided by Atlas is a key part of that story. Now, I want to take a moment to talk about something that doesn't get discussed enough in popular science coverage, the human side of this discovery. Because behind every observation, every data point, every spectrum, there are real people working insanely hard to make these discoveries happen. When 3I divided by Atlas was discovered on July 1st, 2025, astronomers around the world dropped everything. Research programs were put on hold. Precious telescope time was redirected. PhD students worked around the clock analyzing data. Instrument teams scrambled to configure their equipment for observations that weren't in the original schedule. Getting telescope time is incredibly competitive. You write proposals months in advance explaining why your research deserves time on these incredibly expensive instruments. And the approval rates are low. Often only 10–20% of proposals get accepted. So when an unexpected target like 3I divided by Atlas appears, it creates chaos. Schedulers have to shuffle observations. Some approved programs get delayed or canceled. There are tough decisions about priorities. But the community pulled together. Observatories around the world coordinated their efforts. Data was shared freely and quickly. Papers were posted to online preprint servers so that everyone could see the latest results without waiting for the slow peer review process. This is science working at its best. People from different countries, different institutions, different backgrounds, all working toward the common goal of understanding this incredible visitor. And let's not forget the spacecraft teams. The ExoMars team had to quickly calculate whether their orbiter could observe the comet and then reprogram their instruments. The Psyche team, focused on their primary mission to a metallic asteroid, took time to observe 3I divided by Atlas as it passed by. The JUICE team designed an entire observation campaign around the comet. These spacecraft weren't designed with interstellar objects in mind, but the teams found ways to make it work. This is what makes astronomy special. It's not just about the discoveries. It's about the people who make those discoveries happen. The late nights at the telescope, the frustration when the weather doesn't cooperate or the equipment malfunctions, the excitement when the data comes in and shows something unexpected, the collaboration across borders and time zones, the sharing of ideas and techniques. Every spectrum of 3I divided by Atlas, every image, every measurement represents hours or days of work by someone who dedicated their life to understanding the universe. And when you look at the results, this incredible wealth of knowledge we've gained about an ancient visitor from the depths of space, you're seeing the product of human curiosity, ingenuity, and cooperation at its finest. So what's next for 3I divided by Atlas? Right now, as I'm telling you this story, the comet is moving away from the Sunday. It's heading back out into the outer solar system and eventually into interstellar space. It's getting fainter as it recedes, and soon it will be too faint for most telescopes to track. Within a few years, it will cross beyond the orbit of Neptune and keep going. Within a few decades, it will leave our solar system entirely and return to the vast emptiness between stars. This was a brief encounter. 3I divided by Atlas has been traveling through space for billions of years, and its passage through our solar system lasted only a few months. We got lucky. It happened to pass close enough and at the right time for us to observe it with our most powerful instruments. If it had come through even 10 years earlier, we would have missed most of these observations because some of our best instruments like James Webb didn't exist yet. But even as 3I divided by Atlas leaves, its legacy remains. The data we collected will be analyzed for years. Scientists are still working through the observations, finding new details, testing new hypotheses. Papers will continue to be published. PhD students will write dissertations based on this data. The information from those spacecraft observations in November 2025 still hasn't reached Earth. When it does, it will likely reveal even more surprises. And perhaps most importantly, 3I divided by Atlas has changed how we think about interstellar objects. Before Oumuamua, they were theoretical. After Oumuamua, they were real but mysterious. After Borisov, they seemed maybe comprehensible. But 3I divided by Atlas? It's shown us that interstellar space is weirder and more diverse than we imagined. Each new visitor brings surprises. The question now is, what will the fourth interstellar object bring us? And the fifth? And the 10th? Will we find patterns? Will we discover that 3I divided by Atlas's bizarre chemistry is actually common for objects from the galactic thick disk? Or is it an outlier even among ancient comets? We don't know yet. But that's what makes this exciting. We're at the frontier. We're learning something new with each discovery. And unlike a lot of astronomy where we're observing things billions of light years away that we can never hope to visit or study up close, interstellar objects actually come to us. They pass through our neighborhood. They're accessible. There's something poetic about that. The universe is vast and mostly empty, but occasionally, a traveler from distant shores comes wandering through our cosmic backyard, carrying messages from places and times we can barely imagine. And if we're paying attention, if we have the tools and the knowledge, we can read those messages. 3I divided by Atlas is one of those messengers, an ancient wanderer from the galaxy's youth, carrying the chemical fingerprints of a long-dead stellar nursery, showing us how planetary systems can differ across space and time. It reminded us that the universe is full of variety, full of surprises, and that there's always something new to discover. And you know what? That's the real story here. Not whether it might have sent a radio signal 50 years ago. Not whether its chemistry is so weird that it must be artificial. Those make for fun headlines, but they miss the point. The point is that we live in a universe where comets billions of years older than Earth just casually drift by, where chemistry we've never seen before exists out there in the galaxy, where every star system might have its own unique chemical signature based on when and where it formed, where the building blocks of worlds and potentially of life itself are traveling between the stars, mixing and dispersing throughout the galaxy. That's the universe 3I divided by Atlas is showing us. A universe that's far stranger, far more interesting, and far more beautiful than we give it credit for. A universe where nature alone, following the laws of physics and chemistry, can create objects so weird that they challenge our understanding and force us to expand our theories. We didn't need aliens to make this story incredible. Reality did that just fine on its own. Think about the journey this object has taken. It formed in a protoplanetary disk around a star we'll never know in a region of the galaxy that was very different from where we are now. That star system eventually ejected it. Maybe a close encounter with a planet, maybe gravitational interactions with other bodies in the system, maybe the star system itself was disrupted by passing through a dense star cluster. However it happened, 3I divided by Atlas was thrown out into interstellar space, and then it wandered for billions of years through regions of the galaxy we can only imagine, past other star systems, through molecular clouds, maybe through the supernova shockwaves from dying stars, bombarded constantly by cosmic rays, slowly losing the most volatile of its chemicals to radiation damage. All of that time, it was alone. No sun to orbit, no planetary siblings. Just the cold, dark emptiness of interstellar space and the distant glow of the galaxy's stars. And then, by chance, its trajectory happened to intersect with our solar system. After billions of years of wandering, it found itself approaching our Sunday. It warmed up for the first time in ages. Its ices began to sublimate. It developed a coma and a tail. And for a few brief months, it was part of our cosmic neighborhood. We watched it. We studied it. We learned from it. And then it left, continuing its eternal journey through the galaxy. Where will it go next? We can calculate its trajectory, but predicting where it will be millions of years from now is difficult. Gravitational interactions with other stars will slowly change its path. Eventually, it might encounter another stellar system. Maybe in that system, there will be astronomers who detect it passing through. Maybe they'll study it like we did. Maybe they'll wonder about where it came from and what it means. Or maybe it will wander forever, a lonely traveler carrying the memory of a star system that died before life even emerged on Earth. There's something melancholy about that, but also something beautiful. The universe is telling its story through objects like this. Each comet, each asteroid, each wandering planetesimal is a chapter in the history of the galaxy, and we're learning to read those chapters. Before I wrap this up, I want to address something that I think gets lost in a lot of science coverage, especially when it comes to weird discoveries like 3I divided by Atlas. There's often this tension between wanting to make discoveries sound exciting and mysterious and being responsible about not overselling or sensationalizing the results. 3I divided by Atlas is genuinely amazing. Everything I've told you about it is real. The unprecedented mass, the ancient age, the bizarre chemistry, the unusual behavior, all of that is supported by solid scientific observations and published in peer-reviewed papers. This isn't speculation or hype. This is real data showing us something remarkable about the universe. But at the same time, we need to be careful not to jump to conclusions that aren't supported by evidence. Yes, the WOW signal alignment is statistically interesting, but statistically interesting doesn't mean meaningful. Sometimes coincidences are just coincidences. And while it's fine to note the alignment and investigate it, we can't leap from "this is an interesting coincidence" to "this must be artificial" without evidence. The same applies to the unusual chemistry. Yes, organometallic carbonyls can be produced industrially, but they can also form naturally in cold, carbon monoxide-rich environments. Just because a process can be done artificially doesn't mean every instance of that process is artificial. Water can be produced in a factory, but that doesn't mean every raindrop is artificial. Science works by following the evidence and applying Occam's razor. The simplest explanation that fits all the observations is usually correct. And right now, the simplest explanation for everything we observe about 3I divided by Atlas is that it's a natural comet with unusual but explicable chemistry formed under different conditions than solar system comets. That explanation requires no new physics, no unknown processes, no extraordinary assumptions. It just requires acknowledging that the universe is bigger and more diverse than our limited sample of solar system objects would suggest. If future observations show something that can't be explained naturally, then scientists will follow that evidence wherever it leads. But right now, we're not there. And that's okay, because the natural explanation is already incredible. I think sometimes we undervalue how amazing nature actually is. We're so used to looking for the sensational, the mysterious, the potentially alien, that we forget that the universe itself, operating on nothing but physics and chemistry and time, creates wonders beyond imagining. A comet that's been wandering the galaxy for twice as long as Earth has existed. That alone should blow your mind. You don't need to add anything else to make it impressive. The universe has already done the impressive part. So, where does all of this leave us? What's the takeaway from the story of 3I divided by Atlas? I think there are a few key lessons here. First, the universe is far more diverse than our limited perspective would suggest. We live in one solar system, formed at one time, in one location in the galaxy. It's easy to assume that our solar system is representative, that the conditions here are typical. But 3I divided by Atlas proves that assumption wrong. Different times, different places, different conditions lead to different chemistry and different types of objects. The universe isn't uniform. It's a patchwork of different environments, each with its own characteristics. Second, we're just at the beginning of understanding interstellar objects. 3 detected visitors isn't enough to draw broad conclusions. Each one has been dramatically different from the others. Oumuamua with its bizarre shape and acceleration, Borisov looking more normal, 3I divided by Atlas with its ancient origins and exotic chemistry. What will the fourth one show us? We need more data. And fortunately, we're about to get it as new survey telescopes come online. Third, the tools we're developing. Powerful space telescopes like Webb and Hubble, sophisticated spectrometers, networks of ground-based observatories, spacecraft scattered throughout the solar system are giving us unprecedented ability to study these visitors. Every observation campaign teaches us something new and pushes the boundaries of what we know. Fourth, and perhaps most importantly, there's so much we don't know. And that's exciting. Every answer raises new questions. Why is 3I divided by Atlas so massive? How common are ancient comets from the thick disk? What happens to these objects after billions of years of cosmic ray bombardment? How does the chemistry of planetary systems vary across the galaxy's history? These are questions we couldn't even ask before. Now we can ask them, and we have a chance of actually finding answers. The story of 3I divided by Atlas isn't finished. The data from JUICE won't arrive until early 2026. More analysis is ongoing. More papers will be published. And someday, maybe in our lifetimes, we might actually send a spacecraft to intercept an interstellar object and study it up close. But even with what we know now, 3I divided by Atlas has already changed astronomy. It's shown us that the galaxy's past is accessible through these wandering messengers. It's demonstrated that the chemistry of planetary formation varies more than we thought. It's given us a glimpse into conditions that existed billions of years before our world was born. And it's reminded us of something essential, that space exploration isn't just about sending robots to Mars or planning missions to the outer planets. Sometimes exploration means being ready when the universe delivers something to our doorstep. Sometimes the most interesting science comes from being observant, being prepared, and being ready to drop everything when something unexpected appears in the sky. 3I divided by Atlas appeared. We were watching, we were ready, and we learned something incredible. That's the story. An ancient comet from the depths of time and space, carrying chemical secrets from the galaxy's youth, passing through our solar system for a few brief months and revealing wonders we never imagined, breaking records, defying expectations, rewriting textbooks. And somewhere out there, right now, there's probably another interstellar visitor on its way. We don't know when it will arrive. We don't know what it will show us. But when it comes, we'll be ready. Because that's what we do. We watch the sky. We ask questions. We seek answers. The universe is vast and ancient and strange. Objects like 3I divided by Atlas remind us of that. They remind us that we're part of something much bigger than ourselves, much older than our species, much more complex than we can fully understand. But they also remind us that we can understand pieces of it. We can decode the messages. We can read the story written in chemical compositions and orbital trajectories. We can look at a comet that's 7.6 billion years older than Earth and say, I know where you came from. I know what you're made of. I know your story. That's the power of science. That's the beauty of exploration. And that's why discoveries like 3I divided by Atlas matter. The massive new data drop on 3I divided by Atlas has confirmed the rumors and exceeded them. This isn't just another comet. It's a cosmic time machine, a chemical fingerprint from the galaxy's distant past, a messenger from beyond carrying secrets we're only beginning to understand. Every observation revealed something new. Every measurement challenged our expectations, and every answer led to more questions. That's how discovery works. That's how we learn. One cosmic visitor at a time, one observation at a time, one revelation at a time. 3I divided by Atlas came from the darkness between the stars, blazed briefly through our solar system, and returned to the darkness. But it left us with knowledge, with data, with mysteries to solve and questions to answer, with a deeper understanding of how diverse and amazing the universe really is. And honestly, that's worth more than any radio signal or any speculation about artificial origins. The real universe, the natural universe, the universe governed by physics and chemistry and time is incredible enough. Thanks for watching.